Okay, we're on example 2 then with the section on exponential logistic growth. And if we look at this, we have the second part similar. The population P of T of Fish in a lake satisfies the logistic equation that you see here. So these are very similar, right? And so remember in the first problem, we're talking about fish in the lake, and we have P of 0 is equal to 4,000. Same problem here. So we're going to look at it again, and we've got then the limit as t approaches infinity of P of T is still going to be 18,000. It's the same expression. But now the range is going from 1,000 to, I have to remember if I put the equal signs on there. I did not. So let me make sure that I have those on there. So on the ends where we have the range then goes from 10,000, because you're starting at 10,000, and goes to 18,000. So at this case, dPdt is equal to 0, at the same places. And then we can see that, oops, hold on a second. We can see that the function is then increasing. It's increasing on the interval then from 10,000. It's going to behave the same way, 10,000 to 18,000. So the same situation. And it's not decreasing anywhere. Then it's concave down for what values of P of T. So we have the second derivative, P dt, the same thing as before. Then the graph is concave down on 10,000, because you're looking at your interval changing here to 18,000. And does the solution curve have an inflection point? And the answer is no, because it doesn't go through a change. The second derivative doesn't change sign. Doesn't change signs. Okay, so this is what it's going to look like using the information. So if we start off at 10,000 now, if we look at an axis where we start off, I didn't put the 4,000 on the last one, but if I put 18,000 here, 18,000, and here's our leveling off, our asymptote, if you will. So if we start at 10,000, we're past that inflection point where it's concave up and then it became concave down. So our graph then would look like this, as it would level off, and it all has to do with the starting location here. Okay. All right, so that is what happens. So the limit, as we will, as t goes to infinity of this graph of P of T is then equal to 18,000. Okay, so the next one, example 3, we're going to start a little bit differently. So the population P of T inefficiently satisfies the differential equation, same thing. So remember, let me put this here so you can see that. I thought maybe for the last one, dPdt, remember, is 1 over 6,000, where I factored that out. And then I have a P times 18,000. I think it was 18,000 is P, right? Okay. So then when I look at this, and I go, all right, so where t is measured in years and P of 0 is equal to 20,000. So it's above the limiting of 18,000. So then we can take the limit, it's 18,000. And then what is the range of the solution curve? It's going to go from 18,000 and to 20,000. And so put equal here. And then for what values of P is the solution curve decreasing? For what values of P is the solution curve decreasing? So dPdt, this is part C, dPdt is equal to 0 where? Well, we know where it's equal to 0 from the previous problem. Here dPdt is equal to 0 where? Anywhere? Doesn't seem like it's equal to 0 anywhere there, because it's equal to 0 at 18,000 and 0. So you're above at this point. You're going downward, hopefully down to 18,000. Oops, sorry, wrong page. So for this one. So in this case, for what values of P is a solution curve increasing or decreasing? It's simply decreasing. It's going to be pulled back down. It's decreasing on the interval from 18,000 to 20,000. It's an ordering property with intervals. So, and we're talking about the interval for the population. And then for what values of P, so if we say, where is it equal to 0? Is it equal to 0 anywhere on that interval? So we're on the interval from 18,000 to 20,000. So if you remember, the graph is concave up on the interval from 18,000. And this is from the previous page to 20,000. So with that information, we should be able to draw kind of what happens in this situation. Does the solution curve have an inflection point? There's no point of inflection here because the second derivative doesn't change signs. So then using the information to sketch the graph, what it's going to look like is that you're going to start off at P of 0 is equal to 20,000, right? So my graph looks like this. And so we're going to start up here at 20,000. And then this is the 18,000 line. So we're talking about population of fish, so 18,000 fish. And so we're going to start here, and then we're going to go downward, and the graph is going to be concave up, and it'll kind of ride out where this is y is equal to 18k. So the limit as t goes to infinity of p of t is then going to equal 18,000 still, but the graph is concave up and decreasing on the interval. Okay, so that's an introduction to logistics, and we have some more problems tomorrow that we'll be working on. And I tried to keep the problems to the same type, looking at how they're built. But again, the carrying capacity is always like a magnetic effect, like an asymptote. It is an asymptote. And so I thought this would help. And I will see you tomorrow. Have a good night. Bye.